Okay, so the last video about 2.7 inverse functions is going to recognize that not all functions have inverse functions. So one thing we want to consider is think about the function f of x equals x squared. So if I do my process, I get y equals x squared, and then I switch them, so I get x equals y squared, and then when I take the square root to solve, this actually gives me positive or negative square root of x equals y. And if we were to graph that, we would not end up with a function. It would look something like this, and it would fail our vertical line test. It hits at 2 points, and so therefore it's not a function. So one thing that we want to be able to do is we want to identify one-to-one functions. If a function is one-to-one, then it has an inverse function. And a function y equals f of x is one-to-one if no horizontal line intersects the graph in more than one place. So if you think about f of x squared, this is almost treating this like a horizontal line test. So we can test with a horizontal line to see if a function is one-to-one. Now this fails the horizontal lines test, so it is not 1 to 1. Therefore, f of x squared does not have an inverse function. There is an exception. The exception would be if you only were to consider when the x values are greater than or equal to 0. So if I'm only looking at the positive part of x squared, we would be okay. It would only have that 1 point on that horizontal line. But if a function fails the horizontal line test, then it is not one-to-one, and therefore it would not have an inverse function. If it is one-to-one, though, it does have an inverse function. So let's take a look at some examples. We're going to state whether each function graph below is one-to-one. We test that with a horizontal line test. So for this first one, I'm just going to come to each y value that has a point and draw a horizontal line and make sure that it doesn't hit twice. This one is one-to-one. Okay, this one right here, we can clearly see if I draw a horizontal line, it hits multiple times. So this is not 1-to-1. Put big X. Okay, this one right here, horizontal line test. Not perfect, but we can kind of get the gist that for each of these horizontal lines, it only hits once. So this one is 1-to-1. The last big thing about this is being able to graph an inverse function. So we already discussed this a little bit. Essentially, the coordinates, xy coordinates of a function switch for the inverse. Okay, so it states here that if the point AB is on the graph of a function f, then BA is on the graph of the function's inverse. The graph of the function's inverse is a reflection of f about the diagonal line y equals x. So what you want to look for is you want to look for this y equals x line, and you want to see the reflection of this function over that line. So all you got to do is take the coordinates that you have. So let's list them. I'm going to kind of color code them. So this one, it's kind of hard to see, but this first one is -4, -2. Okay. The second one, which I'll do in orange, it looks like it's -3, 1. Okay. This one right here in blue looks like -1, 2. And the last one, which I'll do in black, is 1, 4. So we can actually use those points to find the points of our inverse because we're just going to take the swap for each one of them. So if -4 and -2 is on my function, then on my inverse, I'm going to have -2, -4. So I go to -2, down 1, 2, 3, 4. There we go. If I have -3, 1 on my function, then on my inverse, I'm going to have 1, -3, which would be right here. Okay. If I have the point -1, 2 on my function, then in my inverse, I'm going to have 2, -1. And then lastly, if I have the point 1, 4 on my function, then on my inverse, I'm going to have 4, 1. And then I can connect these, and it's going to be a reflection of that function over the line y equals x. This is really helpful when you're trying to determine if functions are inverses of one another based on the graph. You want to visualize that line y equals x in the graph and imagine it being a mirror and seeing if the function gets like mirrored or reflected over that line. Okay, and if they don't, then it's clearly not the inverse of that function. So, the last thing from that previous page is a fact that actually is pretty important. That because you're switching the x's and the y's, this fact should make sense, right? The domain of the function f would equal the range of its inverse, and the range of the function f would equal the domain of its inverse. And that should make sense because you're switching your x's, which represent your domain, becomes your y's in your inverse, and your range, your y's in your function, becomes your x values in your inverse. And so the range becomes the domain of the inverse, and the domain of the function becomes the range of the inverse. Okay, so lastly, we're going to consider the function f of x equals x plus 7 squared for the domain -7 to infinity, including -7 because it has a bracket there. It asks us to find the inverse of x and state the domain of the inverse. Before I do that, I want to draw a little rough sketch of what the function itself looks like, okay? Because that's going to be really helpful for us to figure out this and the domain of the inverse, okay? So I'm going to draw a little rough sketch. This is just like, let's go back way back to like, I don't know, 2.5. It was transformations of functions. This is just x squared, the parent function for a parabola, shifted to the left by 7. Look at that review in there. So we're going to go backwards to, we're going to call this -7. 6, 5, 4, 3, 2, 1, 0. Okay, so we're at -7. That's where that vertex is going to be. And then we get our parabola. Here we go. So it's telling us that the domain of this, though, is only from -7 to infinity. So this is going to keep going in this positive x direction forever, but it actually stops at -7. It's so that it will pass that horizontal line test. So the function f of x equals x plus 7 squared is not one-to-one from -infinity to infinity, but it is one-to-one over this interval. Okay, so that's why this will have an inverse function. So one thing we can note, though, is that the domain of the function is -7 to infinity. And if we look at this, though, that the range of f is equal to 0 to infinity. And that's going to help us because that essentially tells us that if the range of the function is this, then that means that the domain of the inverse is equal to that. Okay, so we've already answered this part. We got the domain of the inverse is going to be equal to the range of the original function. So we've already answered that first part. The second part would be to then solve for the inverse. Now, one thing to note is because they chose this domain, there aren't going to be the positive or negative square root. So when I do this, when I say rewrite this as y equals x plus 7 squared, and then I switch them, x equals y plus 7 squared, and I take the square root, I no longer have to worry about that positive or negative side because of the domain that we're looking at. So when I take the square root to solve this, I'm going to end up with the square root of x equals y plus 7. Subtract 7 from both sides, and I end up getting that y equals, and this is my inverse, y equals the square root of x minus 7. Okay? So it's going to take that square root function and shift it down by 7. We can replace that y with the f inverse notation, and we get this. Okay, this is going to be really helpful for the last part of your 2.7 homework. But this is it with inverses for now. We just need to be able to know what an inverse is, be able to find an inverse. If I give you a function that's 1 to 1, can you find the inverse? And then know that the domain of the function is equal to the range of its inverse, and the range of the function is equal to its domain. And know that the graphs of inverse functions are reflections over the line y equals x, which actually, now that I listed them all out, sounds like a lot. But the homework isn't too bad, and if you have any questions, please make sure you reach out to me. Thank you.